Welcome to Chapter 3, covering infrared spectroscopy. Unlike UV-Vis, which probes electronic transitions, IR spectroscopy examines molecular vibrations. When molecules absorb infrared radiation, their bonds stretch and bend at characteristic frequencies. This makes IR spectroscopy an excellent tool for identifying functional groups and determining molecular structure. We'll focus on the modern FTIR technique and why it replaced older dispersive instruments. Infrared spectroscopy operates in the electromagnetic region between visible light and microwaves, typically measured as wave numbers from 4,000 to 400 inverse centimeters. When infrared light passes through a sample, bonds that undergo dipole moment changes during vibration absorb specific frequencies. The resulting absorption spectrum shows peaks at frequencies corresponding to different molecular vibrations. This dipole moment requirement is the fundamental selection rule for IR activity. Stretching vibrations involve changes in bond length. Symmetric stretching occurs when bonds stretch and compress together, as in water where both OH bonds lengthen simultaneously. Asymmetric stretching has bonds moving out of phase, as in carbon dioxide, where one C equals O bond lengthens while the other shortens. The spring mass model describes these vibrations mathematically. Hooke's law relates vibrational frequency to the force constant and reduced mass, explaining why stronger bonds and lighter atoms vibrate at higher frequencies. Bending vibrations change bond angles rather than bond lengths. 4 bending modes exist for CH2 groups. Scissoring brings both hydrogens together in the plane. Rocking moves both hydrogens in the same direction within the plane. Wagging moves both hydrogens the same direction perpendicular to the plane. Twisting moves hydrogens in opposite directions out of plane. Bending modes require less energy than stretching, appearing at lower wave numbers, typically between 1,500 and 600 inverse centimeters. FTIR spectrometers use a Michelson interferometer rather than a dispersive monochromator. The beam splitter divides light between fixed and moving mirrors. Recombined light creates an interference pattern called an interferogram. Mathematical Fourier transformation converts this path difference signal into a wave number domain spectrum. FTIR offers major advantages. All wavelengths are measured simultaneously for faster scans, better signal-to-noise ratio through signal averaging, and higher sensitivity for trace analysis. Functional groups absorb at predictable frequency ranges. OH stretching appears broadly at 3,200 to 3,600 inverse centimeters. NH stretching occurs at 3,300 to 3,500. CH stretching falls between 2,850 and 3,000. The strong carbonyl C equals O double bond stretch appears at 1,650 to 1,750. Aromatic C equals C ring stretching shows at 1,450 to 1,600. CO single bond stretching occurs at 1,000 to 1,300. Triple bonds absorb at higher frequencies than double bonds, which absorb higher than single bonds. The IR spectrum divides into 2 regions. The functional group region from 4,000 to 1,500 inverse centimeters contains characteristic peaks for identifying functional groups. The fingerprint region from 1,500 to 400 inverse centimeters shows complex patterns unique to each molecule. Even structural isomers with identical functional groups have different fingerprint patterns. This uniqueness enables molecular identification through database matching, with applications in authentication, quality control, and forensic analysis. Let's interpret ethanol's IR spectrum systematically. The broad peak around 3,300 inverse centimeters indicates OH stretching from the alcohol group. Multiple peaks near 2,900 indicate aliphatic CH stretching from CH3 and CH2 groups. Peaks around 1,450 correspond to CH bending. The strong absorption at 1050 represents CO stretching. The interpretation workflow starts with identifying the broad OH band for alcohols, confirming aliphatic character. then verifying the fingerprint matches database standards. IR spectroscopy has diverse applications across industries. In pharmaceuticals, it verifies drug purity and identifies polymorphic forms. Materials scientists characterize polymers and composites. Environmental monitoring uses IR to detect atmospheric gases like carbon dioxide and methane. Food science applications include detecting adulteration and ensuring quality. ATR, attenuated total reflectance, mode enables direct measurement of solids and liquids without sample preparation, making IR analysis faster and more convenient. Chapter 3 covered IR spectroscopy fundamentals. Key points include: IR probes molecular vibrations through dipole moment changes. Stretching and bending modes occur at characteristic frequencies. FTIR uses interferometry for fast, sensitive measurements. Functional groups have predictable absorption frequencies like carbonyl at 1700 and OH at 3300 inverse centimeters. The fingerprint region provides unique molecular identification. Chapter 4 will introduce Raman spectroscopy, a complementary vibrational technique using light scattering.